Hello all, welcome to EC Electronics. So in this video we are going to discuss about the signal to noise ratio in analog communication system. We'll be discussing about the signal to noise ratio, and also we'll be discussing about the various terms in the SNR or signal to noise ratio, that is noise factors, noise figure, and the noise factor equation when the amplifiers are connected in cascaded form, that is the Friss equation. All these things we are going to see in this video, and also we'll be doing small numerical questions connected with this equations also. Okay, so this is a quick revision of the topics like SNR, noise factor, noise figure, all those things. Okay, so let's see about SNR, noise factors, etc. If you found the video useful, please don't forget to like, share and subscribe. So in today's video we are going to discuss about the signal to noise ratio in communication systems. We'll be seeing the signal to noise ratio in cascaded connections. We'll be also discussing the topics like noise factor, Friss formula, all those things. Okay, so this is a quick revision video of the noise topic in communication systems. Okay, first we are going to see about the signal to noise ratio. Okay, so the signal to noise ratio means it is nothing but the ratio of signal power to noise power. So throughout this video, we will be representing PS by PN, means it is nothing but the ratio of the signal power to the noise power. So we will calculate the signal power and the noise power at the output side totally, and then we will be taking the ratio of it, which will give you the, or which will give us the signal to noise ratio. And it is represented as S by N. Okay. Now let us see what will be the signal to noise ratio when we are going to connect various amplifiers or repeaters generally in a cascaded form. Okay, so we are going to give an input signal which is having a power of PS, and when this signal is getting transmitted through the communication channel, the communication channel is involved with certain losses, right? This losses will affect the channel. There will be certain noises also getting added to the signal. So consider that the noise at each section of the repeater, consider that this is one session, this is one session, this is one session, likewise it will go on. Here I have only considered 3 sessions, but it will go on. Consider that up to M sessions is there. Okay, and for every session the loss inquired is L, and the gain of each amplifier or repeater at various sessions is G. And we have designed the system in such a way that L into G is equal to 1. There is a product of the gain and the loss is equal to 1. So whatever loss is there, the gain is there to compensate for it. Okay. So what will happen when the signal of strength PS is entering to this repeater or this amplifier session? When it passes through the session, there is a loss of L, but due to the gain, we'll get an output signal power as PS only. Okay. Since LG is equal to 1, we'll get at the output of this repeater signal power is PS again. But what will happen? There is a noise power also, which is getting added to the signal. So for this session, the output signal power is PS and the noise power is PN1. Okay. Now this PS, which is at the output of the first repeater or the first amplifier, is being fed to the second stage. Here again, the loss is L and the gain is G. So the output of the second repeater is again PS, but there is also another some noises included with that repeater stage, which is of value PN2. So the total noise power will be now PN1 plus PN2. So what happens to the noise power is it is getting accumulated, but due to the gain of the amplifier, the signal strength or the signal power will remain the same, which is PS exactly at the output, the end output stage also. Okay, but the noise power will get accumulated. So the total noise power we can represent as PN1 plus PN2 plus PN3. If there is M stages, then up to PN. Now consider that all these powers are identical in value. Okay, just for the simplification purpose, we are just assuming that all the noise powers are identical in value. So we will get a value M into PN. That is M times single value. So the total S by N you will be getting as signal power to total noise power. Signal power at the output stage of the mth repeater or mth amplifier will be PS. So it is PS here by MPN, which is a total noise power at the output. Okay, so this is the S by N. Now if you take the dB value, dB in dB, if you want to convert that to dB, you have to take 10 log 10 of this value. Then 10 log 10 of PS by M PN. Now just distributing the 10 log 10, we'll take 10 log 10 PS by PN as one term plus 10 log 10 1 by M as a second term. So we'll split this fraction as PS by M as one term and 1 by M as next term. And we'll separately give 10 log 10 to both the terms. Now this 10 log 10 PS by PN we are going to take as signal to noise ratio of the input side. So signal to noise ratio of output we can write as signal to noise ratio of input minus 10 log 10 M. Now why this minus is because there was a 1 by M. We have taken the 1 by, that is reciprocal, we have neglected by taking a negative sign here. So minus 10 log 10 M. Okay. So this is the total signal to noise ratio when the amplifiers or repeaters are connected in a cascaded format. Okay. So the concept here is due to the gain of the various repeater sessions or stages, we'll get the signal power as same at the output side, but the noise power will get accumulated, due to which we'll get we'll have some losses in the total S by N. The output S by N will be some portion lesser than the input S by N. Okay. So this is the equation for a cascaded connection. Now we'll do a small problem on this. Okay. Let me just remove this first. Okay, so the question is calculate the output S by N in dB for 3 identical links. Okay, so you need to calculate the S by N in dB. We want to calculate the S by N output, and for 3 identical links, means here M value is equal to 3. Given that S by N for any one link is 60 dB. Okay. That is S by N for any one link. So we'll take as S by N input. Okay. So the S by N for any one link is how much it is? 60 dB. So it is directly given in dB. So we can write the equation S by N output in dB is equal to S by N input in dB minus 10 log 10 M. Okay, so this is the equation. Here we need to find the S by N output. S by N input in dB is given, which is 60, and also M value is given, which is 3. So we'll put 60 minus, since it is directly given in dB, you just have to substitute. Okay, 60 minus 10 log 10, 3. Okay, so if you solve it, you will be getting the value as 55.229 dB. Okay. So this is how you calculate the S by N output. So if in the question the S by N value for any link is given, means you have to take it as S by N input, and for that link S by N output will be 52. That is, will be the equation S by N output equal to S by N input minus 10 log 10 M. Okay, and here the answer coming is 55.229 dB. Okay, so this is how you calculate the signal to noise ratio for cascaded connection. Next we are going to see about the terms like noise factor, noise figure, etc. Next we are going to discuss the term called noise factor. Okay, so for defining the noise factor, first let us consider that there is an ideal amplifier and there is a noisy amplifier. Okay, we'll try to write the S by N equation for both the cases. Okay, so first consider that here for the ideal amplifier, the input signal power is PSI and the output signal power is PSO, and that is equal to gain times PSI. Okay, that is the value. Next, okay, I'll write it once again. So PSI. Okay, next consider that here the noise input power is PNI and its value is equal to KT0BN. Okay, so this is the noise power at the input side, where K is a Boltzmann's constant, T is a temperature, T0 is a temperature in Kelvin, Bn is a bandwidth. Okay, next. Here for output noise power Pn0 is equal to gain times, this is for the ideal case, okay. So gain times k T0Bn. So this is the value for the output noise power. Now if you take the S by N at the input side, S by N at input, what will you get? It will be PSI by PNI, right? And its value is equal to PSI by PNI, which is PSI by KT0Bn, right? This is the value of S by N input. Okay, now if you take the S by N output, what will be the value? It will be PS, that is, we are going to take signal to noise ratio at the output side. This is the signal to noise ratio at the input side. So it will be, for output side, PSO by PN0 or PNO, it will be GPSI by G into KT0Bn, right? If you cancel out both the G terms, you will be getting PSI by KT0Bn. Now if you consider, this is one equation, this is equation number 2. Equation 1 is equal to 2, right? So for the case of an ideal amplifier, the signal to noise ratio at the input side will be equal to the signal to noise ratio at the output side. So that is a concept. We are having the signal to noise ratio same for the input side and the output side if the amplifier is a ideal one. But generally, we won't have the amplifiers to work in an ideal way, okay. So this is the case for an ideal amplifier. We'll get the signal to noise ratio at the input side will be signal to noise ratio at the output side. Now let us consider a noisy amplifier and let us take the input signal power as PSI, okay, and the output signal power as PSO, which will be GPSI. This is the output signal power. Now the noise power we are going to take is PNI, right? That is, we are going to take it as KT0Bn, okay. And for the output side PN0, we are going to take F into G into KT0Bn. Now, where F is the noise factor, G is the gain of the system. So here also, even if it is an ideal amplifier also, both the powers, that is signal power and noise power, are getting multiplied by the gain factor. But if it is a noisy amplifier, the noise term will get multiplied by another term which is called noise factor or F, okay. So F into G into KT0Bn, okay. Now if you take the signal to noise ratio of the noisy amplifier, and the noise factor is defined as F is equal to the available signal to noise ratio at input to available S by N at output, okay. So this is the ratio called noise factor, okay. Now here, if you write the noise factor for this noisy amplifier, how can you write the ratio? That is, first you have to take the available S by N at input to available S by N at output. First we will write the S by N at input side. It will be PSI by PNI, right, by available signal to noise ratio at output will be PSO by PNO, okay. Now we'll put the values for these terms and we'll be getting PSI by PNI is KT0Bn into, we'll cross multiply these terms, Pn0 will come at the numerator. So Pn0 will put as it is, because we want to define noise factor in terms of the output noise power. So that's why we are keeping Pn0 or Pno as it is. Next, PSO is G into PSI. Okay, what we have done here is we have cross multiplied this term in the denominator, that is PSO by Pno. We have cross multiplied. We have taken Pno to the numerator. Then we have substituted the value of PSO, which is G PSI. The numerator terms also we have substituted the values. PSI is its value is PSI itself. PNI we have taken as KT0BN. Okay. Next, here we can cancel out these terms PSI and PSI, and noise factor F we'll get as Pn0 by G, that is Pn0 by G into KT0BN. So this is the equation for the noise factor. Okay, so the noise factor F is equal to the output noise power by gain into K, Boltzmann's constant, into T0, temperature, into bandwidth. Okay, so this is the equation for the noise factor, and also we can write the output noise power in terms of the noise factor as Pn0 is equal to F into G K T0BN. Okay, so this is the equation for output noise power in terms of the noise factor. So in order to derive this relation, we have kept Pn0 as it is. Okay, so output noise power is equal to noise factor times G into K T0BN. Okay, so this is the case for a noisy amplifier, and this noise factor, if we express in dB, it is called noise figure. So noise factor in dB, we call it as noise figure. Okay, this term also is important. Okay, next we are going to do a small question on this noise factor. So let's see. Okay, so the question is, so next we are going to do a question on the noise factor or noise figure. So the question is, the noise figure of amplifier is 7 dB. Calculate the output S by N if input S by N is 35 dB. Okay, so the relation is, first I'll write the question. So the noise figure is given to us, which is equal to 7 dB. Then S by N at input is given in dB values, it is 35 dB. We need to find S by N output in dB. Okay, so this is the question. So what is the relation between the noise factor S by N input and S by N output? Noise factor F is equal to S by N input by S by N output. Now if you take the dB values, then you can write F in dB is equal to S by N input in dB minus S by N output in dB. Okay, so this is the relation when we are calculating in dB. So you have to take the difference, that is S by N input dB minus S by N output dB will be the noise figure. So this noise factor in dB, it is called noise figure. Okay, write it here, noise figure. So here directly noise figure is given to us, that is 7 dB equal to 35 dB minus S by N output in dB. So for calculating this, you have to take S by N output in dB is equal to 35 minus 7, which is equal to 28 dB. Okay, so this is how you do question on the noise factor and noise figure. So when the relation is using noise figure, you have to take the difference since it is dB values. But when it is a ratio, you have to take noise factor is equal to S by N input to S by N output. Okay, next we are going to discuss the topic of amplifiers, noise factor or noise factor and amplifiers, and also we'll be discussing the Friss formula. So next we are going to discuss about the noise factor in amplifiers. Okay, so in amplifiers the noise is generated actually due to various components throughout the amplifier. Okay, there are various components in the amplifier, and due to this all components they individually generate noises, and the total output noise will be the sum total of all these noises, right? But for convenience, that is for derivation purpose or for the study purpose, we are imagining that this noise is originating from a source of some equivalent power at the input of the amplifier. Okay, so there will be some noise source. We are considering that there is a noise source kept at the input of the amplifier which is causing the noise. Okay, so the input noise generated from this source is taken as PNI, and that is equal to, we are taking the value as KT0BN. Okay, so this is the noise generated from the source, and also there is a noise contributed by the amplifier stage, and that we are going to take as PNA equal to F minus 1 KT0BN. Okay, so this is the noise generated due to the source, and this is the noise contributed by the amplifier. Okay, so the total noise power at the output side will be PNO is equal to PNI plus PNA, that will be KT0BN plus F minus 1 KT0BN, and you'll be getting the value as F G KT0BN. Okay, since it is at the output side, you have to take into gain times. Okay, so there will be a G term also. So this will be the total noise plus there is into G also. So the PNO, that is the output noise at the amplifier's output side of the amplifier, will be gain times F KT0BN. Okay, where F is the noise factor. Next we are going to discuss about the noise factor when the amplifiers are connected in cascaded form, and also we'll be discussing the Friss formula. So that is, when we derive the noise factor equation, we'll get the Friss formula when amplifiers are connected in cascaded form. Okay, so for this connection or for this explanation, we are only taking 2 stages. Okay, but generally there will be n stages. Okay, so consider that we are going to connect 2 stages of amplifiers together in a cascaded form. The first amplifier is having a gain of G1, second amplifier is having a gain of G2. So the first amplifier is having a gain of G1 and second amplifier is having a gain of G2. The noise factor of the first amplifier or this stage is F1. For this stage, the noise factor is F2. Now consider that for the output of the first stage, okay, that is at this part, the noise power is F1 GKT0BN. Okay, so we have put a noise source in front of this second stage to assume that it is generating this noise power. Okay, so I'll write it here. So this is the noise power F1 GKT0BN. Okay, and this noise power is at the output of the first stage. Okay, so the output of the first stage is producing a noise power of F1 GKT0BN. Okay, we'll put it as PN01. That is the noise power at the output of the stage 1. Since it is output noise power, we are using O, and since it is for the stage 1, we are using 1. Okay, and it is taken as F1 GKT0BN. Okay, next we'll put a source here to indicate this power, or for explaining the generation of this much noise power, we are putting a source here. And also this noise power is being given to the second stage, right? So what happens to the noise power? It will get accumulated, or it will be getting added along the cascaded path. Okay, so here this noise power is given to the second stage, and the second stage is an amplifier itself is also generating some noise power. Okay, so the noise power Pn01 is going to the second stage, and that stage, this amplifier itself is having some noise power, and that its value is F2 minus 1 KT0Bn. Okay, for the previous stage when we have discussed one amplifier stages, there also we have considered that there is a source which is generating some noise power, and there is an amplifier which is contributing some noise also, and the output noise power is the sum of these two. There is an amplifier contributed noise power and the source generated noise power, right? Here also we are taking this as the source generated noise power, and this is the noise power contributed by this second stage amplifier. Okay, so at the input side of this second stage, we have a PN I2. Why it is taken as I? Because it is an input power. Input noise power at stage 2 will be the sum of these two. That is F1 G K T0Bn, which is generated from the source, or it is coming from the stage 1. Okay, in either way you can think. Plus the noise power generated by the second stage amplifier, that is F2 minus 1 into K T0Bn, right? So I'll write for you to be more clear. This is coming from stage 1, and this is generated by stage 2. Okay, stage 2 amplifier. So this is the noise power coming from the stage 1. This is the noise power generated from the stage 2. So this is at the input side. Now when we calculate the output noise power at the output of the stage 2, we'll get PNO2. That will be nothing but gain times this noise power, right? PNI2, right? That is, this is the input noise power, and at the output side, this noise power will be multiplied with the gain times. So gain is G2. So G2 into PNI2. So it will be G2 into F1. So substitute this value. F1 GKT0Bn plus F2 minus 1 into KT0Bn, right? So this will be your total noise power at the output of your stage 2. Now just consider that this is equation 1. Okay, we are just going to derive some equation or some Friss formula. So for that, just take this as equation 1. Now also we know that our overall gain G is equal to G1 into G2. Just keep this thing in mind also. Okay. Now we have already written an equation for the output noise power. That is, this is the output noise power at the stage 2, and we have assumed it to be Pn0. Okay, so Pn0 is equal to F into G1 G2 K T0 Bn. Okay, and this Pn0 is nothing but equal to PnO2, right? So we have taken the noise power at the output side as F G1 G2 K T0 Bn, right? Now we want to derive, what we are actually trying to do is we are going to derive an equation for the total noise factor, which is F, for this cascaded connection in terms of the individual noise factor. That is our aim. Okay, so for deriving that, we have taken the total noise factor of this cascaded connection to be F, and F into G1 G2 K T0 Bn is the total output noise power, and we'll take this as equation 1. Sorry, we'll take this as equation 2, and we know that equation 1 is equal to equation 2. Why? This is the thing which we have taken. This is the thing actually coming to the output side. So here we have taken the noise factor as F, but we know that our noise factor or our total noise is coming from the stage 1 and the stage 2, which will be this. Okay, so 1 is equal to 2. So we are going to equate equation 1 is equal to 2, and while equating you have to consider that one more thing is there. This is G1. Okay, here also G1. Okay, so here it is G1. I've actually made a mistake here also. Okay, this is also G1. Okay, so please try to correct it. Okay, so here the output noise at the stage 1 is F1 G1. It is not G, it is F1 G1 K T0 Bn. Okay, so we'll start from once again, just a brief. So Pn01 is the output noise power at stage 1. It is F1 into, that is its noise factor into gain of that stage into K T0 Bn. Okay, then Pni2 is the input noise power at the input side of stage 2, which will be F1 G1 KT0 Bn plus the noise power contributed by that stage, it is F2 minus 1 KT0 Bn. Okay. Also, the output side, the output noise power will be gain of that stage into the input noise power, which will be G2 into this term. And also, you have to take G1 into G2 is equal to total gain G. Okay. Here, we have taken the total output noise power as F G1 G2 K T0 Bn. So, we have to equate equation 1 with equation 2, and on equating, you will get the formula for total noise factor F is equal to, and the equation will be like this, F1 plus F2 minus 1 by G1. Okay, so this is the case for two-stage cascaded connection. Now, if it is an n-stage cascaded connection, how will be? Let's write. Okay, so this is for the two-stage. Here, the total noise factor F is equal to noise factor of stage 1 plus noise factor of stage 2 minus 1 by the gain of the previous stage. This is the noise factor of second stage, and you have to divide with the gain of the first stage, that is G1. Okay, now let us write the general formula for n number of connections in cascaded form. Okay, so you can write F, that is a total noise factor of a cascaded connection, is equal to F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1 G2 plus F4 minus 1 by G1 G2 G3. So likewise it will go on. So this is the equation for the total noise factor of a cascaded connection, and this equation is very important. Okay, especially if you are preparing for some gate examinations or some quantity examination, this equation you should study. You don't need to study the derivation or how it is coming, but you should study at least this equation. If you want to find the noise factor, sometimes it will be noise factor they will be asking, sometimes it can be noise figure also. Okay, anyway, if you are interested in finding the noise factor of a total cascaded connection, then you have to follow this formula, which is called the Friss formula. F1 plus F2 minus 1 by G1. That is, whenever you are taking the noise factor of a particular stage, that term minus 1 by the previous stage's gain. Okay, so here F2 minus 1 by G1, F3 minus 1 by G1 G2. So it is, as it is going on, you have to take the products of gain in the denominator. Okay, then F4 minus 1 G1 G2 G3, likewise it will go on. Okay, so this is the equation called Friss formula. Next we are going to discuss about the noise temperature and how can we write the noise temperature in terms of the, that is, how can we write the Friss formula in terms of the noise temperature. Okay, we'll directly write it. Okay, so noise temperature okay. So the concept of noise temperature is based on the available noise power equation, which is Pn equal to KT0 Bn. Now consider that an antenna is pointed directly to the sun or to the atmosphere or to the sky. The received noise power is large and the corresponding equivalent noise temperature is well above the ambient temperature of the antenna, and that temperature we'll call as noise temperature. Okay, that is, if I'll explain in simple words, that is, if the received noise power, the noise power received by an antenna, consider that there is an antenna and the noise power received by this antenna is very large, such that the noise temperature caused by this noise is well above the ambient temperature of this antenna, then we call that temperature as a noise temperature. Okay, that is TE is equal to PNA by KBN. Okay, we know that PNA, that is the noise power of the antenna, equal to KT0BN, right? So we'll call it as T0 as TE, that is the noise temperature. Okay, so this is the total noise power received by this antenna. Okay, and that noise power is given by KTEBN, right? This is a general equation for noise which we have used till now. Now the T we can write in terms of noise power as PNA by K into BN. That's what I have written here. Okay, I hope it is clear now. Now how can we write the Friss formula in terms of noise temperature? That is very important. Okay, next I'm going to write the Friss formula in terms of noise temperature. TE is equal to T1 plus T2 minus 1 by G1, sorry, this G1, yeah, G1 plus TE3 minus 1 by G1, G2 plus go. So the only difference is wherever you are writing noise factor, replace it with the noise temperature of that stages. That is, total noise temperature will be TE1 plus TE2 minus 1 by G1 plus TE3 minus 1 by G1, G2 plus TE4 minus 1 by G1, G2, G3. Likewise, it will go on. So this is how the Friss formula will get modified if you are writing it in terms of the noise temperature. Okay, so in this video we have discussed about signal to noise ratio. We have started from the very basics. Okay, we have discussed the signal to noise ratio for cascaded connection. Also, we have discussed about the terms like noise factor and noise figure. We have seen how to write the noise factor concept for an amplifier, and also we have derived the Friss formula, which is a very important equation actually in the noise area. And also we have discussed about noise temperature and how to write the Friss formula in terms of noise temperature. Okay, so if you found this video useful, please do share it with your friends, and if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.